Hold a magnet near your refrigerator and you feel a pull you have known your whole life. Deep inside that magnet, the force comes from particles that are themselves tiny magnets, each one carrying a charge and a kind of spin. One of those particles, a heavy cousin of the electron called the muon, is a slightly stronger magnet than the simplest and most beautiful theory says it has to be. And for more than 20 years, that tiny excess looked like our clearest sign that unknown particles were hiding in empty space. This is the story of that extra magnetism, the thing physicists call G-2, and of how a measurement carried out to 12 digits slowly forced us to admit we had read it wrong. We will build it up one quiet step at a time, starting from what a magnet even is. If you enjoy a slow, careful look at the universe, take a moment to subscribe. The first question is the simplest one. What makes a particle magnetic at all? Think of the magnet on your refrigerator door. You can feel it grab the metal before it even touches, a small invisible insistence in your fingers. That pull has a source, and the source is far smaller than anything your eyes will ever see. Inside the iron of that magnet, countless particles are each behaving as a magnet of their own, and when enough of them line up in the same direction, their tiny pulls add together into something your hand can feel. The particle doing most of the work is the electron. Every electron in that magnet behaves as if it were a minuscule bar magnet, with a north end and a south end. Iron is special because its electrons can be coaxed into pointing the same way and made to stay there. In most materials, the little magnets point in all directions and cancel out, which is why your wooden table and your coffee mug do not cling to the fridge. Line the electrons up, and the material becomes a magnet you can hold in your hand. So where does a single electron get its magnetism in the first place? The oldest clue is a simple fact, noticed by Hans Christian Ørsted and made precise by André-Marie Ampère in the early 1800s. A moving electric charge makes a magnetic field. Run a current through a wire, and a nearby compass needle will swing aside. Coil that wire into loops and you have built an electromagnet, the kind that lifts cars in a scrapyard. Moving charge and magnetism are two faces of one thing. An electron carries electric charge, the very same charge that flows through the wire, just bottled up in one tiny package. If an electron were a little ball of charge that spun, it would be a loop of current in miniature, and it would make a magnetic field for the same reason the coil does. That picture is where our keyword comes from. Physicists call the strength and direction of a particle's built-in magnetism its magnetic moment. The magnetic moment is simply how strong a magnet the particle is and which way it points. Here is the gentle place where the everyday picture begins to strain. An electron is, as far as anyone has ever been able to measure, a true point. It has no size, no surface, no little equator to spin around, and yet it has a magnetic moment as real as the one in any compass needle. The spinning ball gives the right flavour and the wrong mechanism, and holding both of those at once is the first real step into this story. For now, keep the flavour. A particle with charge and a property called spin behaves like a tiny magnet, and the size of that magnet is its magnetic moment. This is true of the electron, and it is just as true of the heavier particle this whole story circles around, the muon. The muon is a little magnet too, and measuring exactly how strong a magnet it is will turn out to be one of the most demanding things human beings have ever attempted. You can already feel the shape of the question ahead. If we want to know the muon's magnetism with great care, we first need to know how much magnetism a particle's spin is supposed to produce. We need a number that ties the spin to the magnetic moment, a conversion between the two. That number has a name and a long history, and pinning it down to the last digit is the quiet drama of everything that follows. So we begin with a pull you can feel in your hand, and follow it down to a single point of charge carrying a property we have not yet explained. That property is spin, and it is stranger and far more important than the image of a spinning ball lets on. In 1922, two physicists in Frankfurt sent a thin beam of silver atoms through a specially shaped magnetic field and watched where the atoms landed on a glass plate. Their names were Otto Stern and Walter Gerlach, and what they saw should not have been possible under the physics of their day. The beam did not spread into a smooth smear, as a collection of ordinary little magnets pointing in random directions would. It split cleanly into two, one spot high and one spot low with nothing in between. That split was telling them something deep. The silver atoms were behaving like magnets, which was expected, but the direction of each magnet could only take one of two values along the field, up or down, and nothing in the middle. The magnetism was not free to point anywhere. It came in fixed, separate steps. In the language that was just then being born, the magnetism was quantized. A few years later, in 1925, two young Dutch physicists named Samuel Goudsmit and George Uhlenbeck found the property hiding behind that split. They proposed that the electron carries a fixed amount of angular momentum all its own, a built-in twist that has nothing to do with moving through space. They called it spin, because the only familiar thing that carries angular momentum is a spinning object, and the name stuck even though it is a little misleading. It is misleading because the electron cannot literally be spinning. If you take the electron's known magnetism and ask how fast a tiny ball would have to turn to produce it, the surface of that ball would have to move faster than light, which nature does not allow. And the electron, as we said, has no measurable size to spin in the first place. Spin is not motion. It is a property the particle simply has, the way it has charge and mass woven into what the particle is. So you can hold this picture, as long as you remember where it stops fitting. Imagine each electron carries a tiny arrow, fixed in length, that can point up or down along whatever magnetic field it sits in. The arrow is its spin. Because the electron also carries charge, that spin comes bundled with magnetism, and the arrow points the same way the little magnet does. The Stern and Gerlach beams split in two because each silver atom's outer electron could only set its arrow one of two ways. This is why a single point of charge can be a magnet without spinning. The magnetism rides on the spin, and the spin is intrinsic. Every electron in the universe has exactly the same amount of it, a value physicists write as 1/2 in their counting system, which is why we call the electron a spin 1/2 particle. The muon, our heavier character, is also spin 1/2. In this one respect, the muon and the electron are identical twins. The discovery of spin reshaped physics. It explained the structure of the periodic table, the colours of light that atoms give off, and eventually the very stability of matter, since two electrons with the same spin cannot crowd into the same place. For our purposes, though, spin matters for one reason above all. It is the source of the particle's magnetism, the thing that makes an electron or a muon a tiny magnet at all. And that brings us back to the conversion we still owe ourselves. We have a particle with a fixed spin and a definite magnetic moment. The question is, how strongly the one produces the other. How much magnetism comes from a given amount of spin? The answer is a single dimensionless number, and almost everything that follows is a story about measuring that number to the very edge of what is possible. To turn spin into magnetism, you need a conversion factor, and physicists gave that factor a plain name. They call it the G factor. The G factor is the number that says how strong a magnet a particle is for a given amount of spin. A larger G means more magnetism wrung from the same twist. It is one of those quiet quantities that looks like bookkeeping at first, and turns out to hold a universe of physics inside it. To feel why a factor is needed at all, go back to the only kind of magnet that classical physics fully understood, a loop of electric current. If you take a ring of charge and set it physically spinning, it has angular momentum from the orbiting charge, and it makes a magnetic field. For that ordinary case, the magnetism and the angular momentum march together in a fixed, simple ratio. Doubling the spin doubles the magnetism, cleanly and proportionally. If the electron's magnetism worked the same way, its G factor would come out to 1. When physicists actually measured the electron, the number was not 1. It was close to 2. The electron is twice as magnetic as the naive picture of an orbiting charge would predict, for the same amount of angular momentum. Spin magnetism is, in a sense, doubly efficient, and nobody in the 1920s could say why. The value simply had to be put in by hand to match experiment, a stubborn 2 sitting in the equations with no explanation behind it. That factor of roughly 2 is the heart of the whole tale, so it is worth slowing down on. Whenever you see physicists write about G, they mean this conversion between a particle's spin and its magnetism. For the electron and the muon alike, G sits very near 2. The story of this video is, at bottom, the story of how near and of the small surplus by which G exceeds 2, and of what that small surplus is trying to tell us about the deepest workings of nature. You can already guess that the surplus will be tiny. The G factor is not 3 or 5, it is 2 plus a sliver. But in physics, a sliver measured precisely enough can be worth more than a mountain measured roughly, because the sliver is where the subtle effects hide. A theory that is almost right will get the 2. Only a theory that is exactly right will get the sliver too. It helps to give the sliver its own name now, because we will lean on it for the rest of the journey. Physicists define a quantity they call the anomaly, written with a small letter a. The anomaly is just the amount by which G rises above 2, cut in half by convention so that it equals G minus 2 divided by 2. When G is exactly 2, the anomaly is 0. When G is a hair above 2, the anomaly is a small positive number, and that number is what every experiment in this story is really chasing. The name G2 that you may have heard, the name carried by the great experiments at Brookhaven and Fermilab, comes straight from this. It is shorthand for G minus 2, the surplus above the simple value. An entire field of physics is named after a subtraction. So we now have the question in its sharpest form. A particle's spin makes it a magnet, and the G factor measures the strength of that magnet. The simple expectation gives 1, experiment gives 2, and the truth is 2 plus a whisper. To understand the whisper, we first have to understand the 2, and the man who finally explained the 2 did it with one of the most beautiful equations ever written. In 1928, a quiet, intensely private Englishman named Paul Dirac set himself a problem that the best minds of the day had set aside as too hard. Quantum mechanics, only a few years old, described slow particles well. Albert Einstein's special relativity described fast ones, but the two did not yet fit together into a single equation for the electron, and the electron, light and easily pushed to high speeds, plainly needed both. Dirac wanted one equation that obeyed quantum rules and relativity at the same time. The way he worked was unusual. He was after mathematical beauty as much as physical fit, trusting that an equation simple and consistent enough would turn out to be true. After months of effort, he found it, a compact relation now known simply as the Dirac equation. It is short enough to write on the back of an envelope, and it changed physics permanently. What makes the equation extraordinary is what it gives you for free. Dirac did not put spin into it by hand. He was only trying to make the electron obey relativity and quantum mechanics together. Yet when he worked out what his equation implied, spin came tumbling out on its own, with exactly the value 1/2 that experiments had found. The property that Goudsmit and Uhlenbeck had to propose as a guess fell straight out of the mathematics as a necessity. The electron had to have spin, because relativity and quantum mechanics together demanded it. And there was more. The equation also predicted the electron's G factor, the conversion between spin and magnetism that had stubbornly refused to be explained. Out of Dirac's equation came the value 2, precisely and without adjustment. The mysterious factor that physicists had been forced to insert by hand was simply there, baked into the structure of a relativistic quantum electron. For the first time, the doubled magnetism of spin had a reason. It is hard to overstate how clean this result is. Dirac was not fitting data. He was following the logic of two principles, and the doubled magnetism appeared as a theorem. A point particle of spin 1/2, obeying his equation, must have a G factor of exactly 2, not approximately 2, exactly. The simplest complete theory of the electron makes a sharp, unconditional prediction, and that prediction is the round number at the centre of our story. The same equation held one more surprise. It had solutions that seemed to describe a particle just like the electron but with the opposite charge. Dirac, after some hesitation, took these seriously and predicted a mirror partner, what we now call the positron, the electron's antimatter twin. A few years later, Carl Anderson found exactly such a particle in cosmic rays, and Dirac's faith in the beauty of his equation was vindicated again. The same Carl Anderson we will see shortly was about to stumble onto the muon as well. For now, hold tight to the clean prediction, because it is the baseline against which everything will be measured. Dirac says G equals 2, a perfect, isolated, point-like spinning charge alone in empty space should have a magnetic strength of exactly 2 in these units and an anomaly of exactly 0. If you measured such a particle and found G to be 2 on the nose, the theory would be complete and the story would end here. But that is not what we find. Real electrons and real muons have a G factor slightly above 2. The whisper is there. And the reason the whisper is there is that no particle is ever truly alone in empty space, because empty space, as the next steps will show, is not empty at all. Before we get there though, we need to meet the muon properly, the heavier cousin whose magnetism we have come to weigh. In the mid-1930s, physicists studied the rain of particles that pours down on the Earth from space, the cosmic rays. To catch them, they used a cloud chamber, a sealed box of cold vapour in which a fast-charged particle leaves a thin trail of droplets, like the line a jet scratches across a clear sky. By placing the chamber in a magnetic field and watching how sharply each track curved, they could read off the particle's charge and weigh it, since a heavier particle bends less. In 1936, working at the California Institute of Technology, Carl Anderson and his student Seth Neddermeyer found tracks that made no sense. The curving showed a particle with the charge of an electron, but it bent too gently to be an electron and too sharply to be a proton. Its mass sat in between, around 200 times the electrons and far less than the protons. It was something new, a middleweight particle nobody had ordered. At first there was confusion about what it was. A few years earlier, the Japanese physicist Hideki Yukawa had predicted a particle of roughly this mass to carry the force that binds the atomic nucleus together. For a while, people thought Anderson's particle was Yukawa's. It was not. Careful experiments showed that the new particle barely felt the nuclear force at all, passing through matter far too easily to be the glue Yukawa had in mind. The nuclear particle, the pion, was found later and turned out to be a different thing that decays into Anderson's particle. What Anderson and Neddermeyer had actually found we now call the muon. It is a genuinely strange guest at the table of physics because it appears to be nothing more than a heavier copy of the electron. It has the same electric charge as the electron. It has the same spin, 1/2. It feels the same forces in the same ways. The single clear difference is its weight. The muon is about 207 times as heavy as the electron, and otherwise it is the electron's near-perfect twin. This needless duplication baffled everyone. The physicist Isidor Isaac Rabi, on hearing that nature had simply made a fatter electron for no apparent reason, is said to have asked, "Who ordered that?" The line has lasted because it captures the genuine puzzlement. The electron was understood. The proton and neutron built the nucleus. The muon fit no need. It was an extra, and decades later we still cannot fully say why the universe bothers to include it, along with a third, heavier cousin called the tau. The muon also differs from the electron in one practical way. It does not last. A muon at rest survives for only about 2/millionths of a second before it decays, breaking apart into an electron and a pair of nearly invisible particles called neutrinos. That fleeting lifetime sounds like a fatal problem for any careful measurement. A particle that vanishes in microseconds seems impossible to study at leisure. We will see that physicists turn this very weakness into the tool that reads the muon's spin, but that is a step still ahead. So the muon arrives as a heavier, short-lived double of the electron, sharing its charge and its spin, and therefore, like the electron, behaving as a tiny magnet with a G-factor near 2. Everything Dirac said about the electron applies to the muon as well. Its simplest predicted G-factor is exactly 2, and its real one is a whisper above. The natural question is why we should go to all the trouble of weighing the magnetism of this fragile, redundant particle, when the electron is right there, stable and easy to hold. The answer is surprising, and it turns the muon's heaviness from a curiosity into its greatest gift. The reason to chase the muon rather than the electron comes down to a single idea, and it is one of the loveliest in the whole subject. A particle's magnetism is sensitive to everything that can momentarily touch it, including particles too heavy to ever see directly. And a heavier probe feels heavy influences far more strongly than a light one does. The muon, being more than 200 times heavier than the electron, is a much more sensitive listener for the faint voices of massive unknown particles. To get a feel for this, picture 2 tuning forks, a small light one and a large heavy one. Tap them and they ring at different pitches. Now imagine some faint deep hum in the room that you cannot hear directly. The heavy fork, tuned closer to that low register, will pick up and answer the hum far more readily than the dainty one. In the same way, the electron and the muon are 2 probes tuned to different scales, and the heavier muon resonates with heavy effects that the electron barely notices. The mathematics behind this is clean. The pull that a heavy unknown particle exerts on a lepton's magnetism grows with the square of the lepton's mass. The muon is about 207 times heavier than the electron, and 207 squared is a little over 40,000. So the muon is roughly 40,000 times more sensitive than the electron to whatever heavy particles might be lurking in the vacuum. A new force, or a new particle that would shift the electron's magnetism by an amount too small to detect, could shift the muons by an amount you can actually measure. This is why the muon, the redundant particle nobody ordered, became one of the most important objects in modern physics. Its anomaly, the small surplus of its G-factor above 2, acts as a kind of sensitive scale. Onto that scale climbs every particle that can briefly interact with the muon, including ones we already know, and, possibly, ones we have never seen. If our list of known particles is complete, theory and experiment for the muon's magnetism should agree perfectly. If something is missing from the list, the muon's anomaly is one of the best places to catch it tugging. There is a cost to this gift, and we have already met it. The muon lives for only about 2/millionths of a second. The electron is forever, which is why the electron's magnetism can be measured with even greater raw precision by trapping a single one and watching it for months. The muon will never sit still that long. To weigh its magnetism, physicists had to invent a way to read a particle's spin in the brief flash before it dies, and to do it not to 1 muon but to billions, over and over. So a trade sits at the centre of this story. The electron offers stillness and the ultimate precision, but it is a poor listener for heavy new physics. The muon offers a far better ear for the unknown, but it forces you to work fast and clever against the clock of its own decay. For the question that matters most, whether our theory of particles is complete, the muon is worth the trouble. Hold this as the reason for everything that follows. The muon is a magnifying glass for the hidden. Its small excess of magnetism is amplified by its heaviness into a signal we can hope to read, and that signal carries word of whatever shares the vacuum with it. And it is to the vacuum that we now must turn, because the entire reason a real muon's G-factor climbs above Dirac's clean value of 2 is that the muon is never truly alone. The space around it is alive. Empty space sounds like the simplest thing imaginable. Remove every atom, every speck of light, every trace of matter, and you would expect to be left with pure nothing, a perfect stillness. For most of the history of physics, that is exactly what people assumed. The vacuum was the empty stage on which the play of particles happened, itself featureless and inert. Quantum mechanics took that stage and made it tremble. The trouble starts with a rule discovered by Werner Heisenberg, the uncertainty principle. Among other things, It says that energy cannot be pinned down perfectly over a very short stretch of time. For a fleeting instant, energy can flicker into existence and vanish again, as long as it pays back the debt fast enough. Over the briefest moments, the books need not balance, and nature exploits this freedom relentlessly. What flickers into existence are particles in matched pairs of matter and antimatter. An electron and a positron can appear out of the vacuum, exist for a sliver of time too short to ever catch directly, and then annihilate back into nothing. Photons, the particles of light, wink in and out as well. These short-lived flickers are called virtual particles, and they are not a figure of speech. They are a constant, seething froth filling all of space, even space we would call perfectly empty. The everyday picture to hold is the surface of a pot of water just before it boils. From a distance, the surface looks flat and still. Up close, it is alive with tiny bubbles forming and collapsing, a restless shimmer that never stops. The quantum vacuum is like that, except the bubbles are particles and antiparticles, appearing and vanishing everywhere, all the time. Where the comparison breaks down is that the vacuum's froth needs no heat and no container. It is the lowest, calmest state space can have, and it still churns. We're not guessing about this. The activity of empty space leaves fingerprints we can measure. In 1947, Willis Lamb found a tiny shift in the light emitted by hydrogen, the Lamb shift, that could only be explained by the atom's electron interacting with the vacuum's flicker. The Dutch physicist Hendrik Casimir predicted that two metal plates held very close together in a vacuum would feel a faint attraction, because the froth between them is slightly suppressed compared to the froth outside. That Casimir force has since been measured directly. Empty space pushes on things. Now bring a muon into this restless sea. The muon does not glide through serene nothingness. It is constantly emitting and reabsorbing virtual photons, constantly surrounded by virtual pairs winking into being and out again. It wears the vacuum's froth like a shifting cloak, and here is the crucial point for our story. That cloak of flickering particles slightly changes how the muon responds to a magnetic field. It nudges the muon's magnetism away from the bare value that Dirac's lonely, undressed particle would have. This is the origin of the whisper above too. Dirac's equation describes an idealized muon utterly alone in true emptiness, and for that imaginary particle G is exactly 2. The real muon is never alone. It is dressed in the constant activity of the vacuum, and that dressing adds a small extra contribution to its magnetism. The G factor climbs above 2 by a tiny amount precisely because empty space is not empty. So the anomaly, the surplus we have been circling since the start, is in a real sense a measurement of the vacuum itself. Every kind of particle that can flicker into the froth around the muon leaves its mark on that surplus. The known particles contribute their share in amounts we can try to calculate, and if any unknown particle exists, light enough to flicker into the cloak, it would add its own small contribution too. The first person to calculate any of this, to take the vacuum's flicker and turn it into a precise number for the surplus, did it in 1948, and his result was so clean it ended up carved on his grave. In the years right after the Second World War, 3 physicists working separately cracked the problem of how to calculate the way charged particles interact with light and with the vacuum. They were Julian Schwinger in the United States, Richard Feynman also in the United States, and Shinichiro Tominaga in Japan, who had done much of his work in wartime isolation. The theory they built is called quantum electrodynamics, or QED, and it is the most precisely tested theory in all of science. The 3 would share the Nobel Prize for it. Julian Schwinger was a prodigy of legendary intensity, a man who reportedly worked through the night and lectured without notes in flawless, finished sentences. In 1948 he turned the new theory on the very question we have been building toward. He asked what the simplest piece of the vacuum's froth does to an electron's magnetism. He considered the most basic interaction possible, in which the electron briefly emits a single virtual photon and then reabsorbs it, all while sitting in a magnetic field. That one process, the electron tossing a photon to itself, slightly increases its magnetism. Schwinger calculated by exactly how much. The answer came out as a beautifully simple expression: the fine structure constant divided by 2 times pi. The fine structure constant is a fundamental number that sets the strength of the electromagnetic force, roughly 1 part in 137. Divide it by 2 pi and you get a tiny number, a little over 1 part in 1,000. That tiny number is the anomaly, the surplus of g above 2 for its leading piece. Schwinger had shown that the g factor is not exactly 2 after all. It is 2 plus that small correction, and the correction comes directly from the simplest flicker of the vacuum. The mysterious whisper now had a calculated value, and it agreed with what experiments on the electron were beginning to show. The vacuum was not only real, it was something you could compute. The result is so elegant that Schwinger asked for the formula to be engraved on his headstone, and it is there to this day, the symbol for the anomaly set equal to the fine structure constant over 2 pi. Few equations earn that kind of devotion. This one did because it marked the moment the unseen activity of empty space became a matter of arithmetic, checkable against nature to many decimal places. It is worth being clear about what Schwinger's number is and is not. It is the first and largest of the vacuum's corrections, the contribution of the single simplest process. It is not the whole story. The vacuum can do more complicated things than toss 1 photon. It can toss 2, or 3, or briefly conjure heavier particles, each a rarer and smaller effect. Schwinger had computed the first rung of a tall ladder, and the rungs above it would occupy physicists for the next 70 years. For our muon, the logic is identical. The muon, dressed in the same froth, gets the same leading correction from emitting and reabsorbing a single virtual photon. To this first level of detail, the muon's anomaly and the electrons are the same small number, Schwinger's number, because this simplest process does not care how heavy the particle is. The differences between the 2 leptons only appear when you climb to the higher, subtler rungs, where the muon's heaviness starts to matter. So by 1948, the shape of the problem was set. The g factor is 2 from Dirac, plus a stack of vacuum corrections, of which Schwinger found the first. Calculate every rung of that stack precisely enough, and you have a prediction. Measure the muon's magnetism precisely enough, and you have a test. The agreement or disagreement between the 2 is the whole game, and to play it, theorists first had to learn to climb the ladder. Richard Feynman gave physicists a way to keep track of the vacuum's ever more complicated antics, and it turned a forbidding tangle of mathematics into something you could almost draw with a pencil. His invention is the Feynman diagram, a simple picture in which straight lines stand for particles like the muon, and wavy lines stand for photons. Each diagram represents one possible thing the vacuum can do, while the muon sits in a magnetic field, and each one corresponds to a precise mathematical term you must calculate. The leading diagram is Schwinger's, the muon emitting and reabsorbing a single virtual photon, drawn as a simple arch over the muon's path. To go further, you draw every more complicated picture you can. The muon emits 2 photons that cross. A virtual photon briefly splits into an electron and positron pair before being reabsorbed. The loops multiply, the diagrams sprout extra arches and bubbles, and each new layer of complication is called a higher order in the calculation. The saving grace is that each extra loop makes the contribution much smaller. Every additional photon in a diagram brings another factor of the fine structure constant, that number near 1 part in 137. So a 2-loop diagram is roughly 100 times smaller than a 1-loop diagram, and a 3-loop diagram smaller still. The corrections shrink as you climb, which means you can stop at a given rung and know your error is no larger than the first rung you left out. The ladder converges, and that is what makes the whole enterprise possible. It does not make it easy. The number of diagrams explodes as you climb. At the first order there is essentially 1. By the time you reach the 5th order, The level physicists call 10th order in their counting. There are more than 12,000 distinct diagrams, each demanding a fearsome integral. No human could ever evaluate them all by hand. This is a calculation that required computers and decades, and a particular kind of patience that borders on devotion. The person most associated with that patience is Toichiro Kinoshita, a Japanese-American physicist who spent much of his long career pushing the QED calculation of the anomaly to ever higher orders. Working with colleagues and generations of improving computers, Kinoshita carried the electrons and muons QED contributions up through that staggering 10th order level, taming tens of thousands of integrals. He continued this work into his 90s. It is a quiet example of a scientific life given to getting one number exactly right. For the muon, the climb has an extra feature that the electrons does not. Some of the diagrams involve a heavier particle flickering in a loop, and how much such a diagram contributes depends on the mass of the particle in the muon's neighbourhood. Because the muon is heavy, certain loops that are negligible for the electron become meaningful for the muon. This is the same heaviness that makes the muon a better probe, showing up now inside the calculation itself. By the end of this effort, the purely electromagnetic part of the muon's anomaly was known to extraordinary depth, with an uncertainty far smaller than anything the experiments could yet test. The QED contribution is the largest piece of the whole prediction, and also the most trustworthy computed term by term, diagram by diagram, checked and rechecked across independent groups. When physicists worry about the muon's magnetism, they do not worry about this part. Before we can trust this towering calculation for the muon, though, it helps to see it pass an even harder test, one where the experimental precision is finer than anywhere else in science. That test is the electron, and the agreement there is so close it has become a kind of touchstone for what physics can achieve. The electron offers something the muon never will, the chance to study a single particle at rest for as long as you like. A stable electron can be caught and held in a device called a penning trap, a small arrangement of electric and magnetic fields that pins one lone electron in place inside a chilled chamber. There, isolated and patient, a single electron can be coaxed into revealing its magnetism with a precision that beggars belief. The physicist Hans Damelt pioneered these traps, and later Gerald Gabriels and his collaborators refined them into the finest magnetism scales ever built. What they measure is the electron's G-factor, the same conversion between spin and magnetism we have followed all along. By watching how a trapped electron's spin and motion respond to the fields around it, they read off the value of G to an astonishing number of digits. The measured anomaly of the electron is now known to better than 1 part in a trillion, a precision so fine it is hard to find anything in daily life to compare it to. It is like measuring the distance from New York to Los Angeles, and being sure of the answer to within the width of a single human hair, and then some. On the other side stands the calculation, the towering stack of Feynman diagrams that Kinoshita and others climbed for the electron. When you take the theoretical value, built from QED to that 10th order, and lay it beside the measured value from the trap, the two numbers agree digit after digit after digit. They match to roughly 12 places. This is the most precise agreement between a prediction and a measurement anywhere in all of science, the closest humanity has ever come to checking a theory against reality and finding no seam. It is worth pausing on what that agreement means. It tells us that QED, the theory of charged particles and light born in the 1940s, is correct to a degree almost beyond comprehension. It tells us the vacuum really does behave the way the diagrams say, and it tells us that the whole method, the climbing of the ladder of loops, genuinely works, that you can compute the unseen froth of empty space and trust the answer to the 11th decimal place. This is the foundation of confidence on which the muon story rests. When physicists turn the same machinery onto the muon, they are not using an untested tool. They are using the single best verified calculational method in physics, one that has already passed the most stringent exam imaginable on the electron. Whatever happens with the muon, no one can dismiss the QED part as shaky. It is the firmest ground we have. The electron's perfect match also pays a practical dividend. Because QED is so well understood and the measurement so precise, the comparison can be run in reverse. Physicists use the electron's anomaly to extract the best value of the fine structure constant itself, that fundamental number near 1 part in 137. The electron is so well behaved that it serves as a ruler for one of nature's basic constants. So why does the electron not show us new physics, if its measurement is even finer than the muons? The answer is the trade we met earlier. The electron, being light, is a poor listener for heavy unknown particles. Its anomaly is measured beautifully and predicted beautifully, and the two agree, which is exactly what you expect from a probe too dainty to feel heavy newcomers. Its silence is consistent with our theory being complete, but it is not sensitive enough to test that completeness severely. The muon is the severe test. It carries the same trustworthy QED foundation, magnified by its heaviness into sensitivity the electron lacks. But the muon's full prediction is not QED alone. Two more forces leave their mark on it, and one of them is about to become the source of all the difficulty. When physicists assemble the full theoretical prediction for the muon's anomaly, they are really adding up the contributions of every kind of particle that can flicker into the vacuum's froth around it. Those particles answer to the known forces of nature, and so the prediction splits naturally into 3 parts, one for each kind of contribution. The first part is the QED piece we have just praised, the electromagnetic effects of photons and light leptons. It is the largest by far and the most reliable. The second part comes from the weak nuclear force, the force behind certain kinds of radioactive decay. Its carrier particles, called the W and the Z, are heavy, and a heavy particle is a rare and feeble visitor to the muon's cloak. So this electro-weak contribution is small, a tiny correction far down in the digits. But it is calculable with good confidence because the weak force, like electromagnetism, is well understood and behaves gently enough to be handled by the same diagram-by-diagram method. The third part comes from the strong nuclear force, the force that binds quarks into protons and neutrons and holds atomic nuclei together. This is the hadronic contribution, named for the hadrons, the family of particles built from quarks. In size, it sits between the other two, much smaller than QED but larger than the electroweak piece. In difficulty, it stands entirely alone. The strong force does not yield to the neat ladder of shrinking corrections that tamed the other two. Here is the heart of the matter stated plainly. The total prediction for the muon's anomaly is the sum of these 3 pieces: electromagnetic, electroweak, and strong. 2 of the 3 can be calculated to a precision that comfortably exceeds what experiments can measure. The third, the strong force piece, cannot be calculated nearly so well, and so it carries by far the largest uncertainty in the whole prediction. When physicists argue about what the standard model predicts for the muon, they are almost always arguing about this one stubborn piece. This is a crucial thing to carry forward because it reshapes the entire detective story. For years, the muon's measured magnetism appeared to disagree with the predicted value, and the natural, thrilling reading was that some unknown particle was tugging on the muon, a hint of physics beyond everything we know. But a disagreement between measurement and prediction can have 2 sources. It can mean the measurement is sensing something new, or it can mean the prediction is simply wrong, because the hard part was miscalculated. The strong force piece is where that second possibility lives. If the hadronic contribution had been computed a little too small, the predicted anomaly would come out too low, and the muon would seem more magnetic than theory allowed, exactly as if a new particle were present. The signature of missing physics and the signature of a mismatched calculation can look almost the same from the outside. Telling them apart is the whole challenge of the modern story. So the muon's anomaly is a sum of 3 voices, and the uncertainty in that sum is dominated by the one voice we struggle to compute, the voice of the strong force. The QED part is solid as bedrock. The electro-weak part is small and well understood. The hadronic part is where the difficulty, and therefore the possibility of being wrong concentrates. We will give each of these three pieces its due. The small electro-weak whisper is the easiest to dispatch, a real and measurable mark left on the muon by the heaviest forces in the everyday standard model. Understanding it shows just how complete and sensitive this single number really is, and it sets the QED and electroweak parts firmly aside so that we can face the strong force, which is where everything in this story will eventually turn. The weak nuclear force is the quietest of nature's forces in daily life, but it runs some of the most important machinery in the universe. It is the force that lets one kind of particle change into another, and that change is what powers the sun. Deep in the solar core, protons turn into neutrons through the weak force, a step without which hydrogen could never fuse into helium and the sun could never shine. The same force governs many forms of radioactive decay, including the decay of the muon itself. The weak force is carried by three particles, the positively charged W, the negatively charged W, and the neutral Z. Unlike the photon, which has no mass and can reach across a room, these carriers are enormously heavy, each about 80 to 90 times the mass of a proton. A force carried by such heavy particles has an extremely short reach and makes itself felt only feebly, which is why the weak force seems so weak at the scales we live in. In the late 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg wove the weak force and electromagnetism into a single framework. The electro-weak theory and the W and Z particles were found at CERN in 1983, just where that theory said they would be. The muon feels this force, and so the W and the Z leave their mark on its magnetism. In the vacuum's froth around the muon, a W or a Z can briefly flicker into being, just as a photon can. When it does, it nudges the muon's anomaly by a small amount. The Higgs boson, the particle tied to how all these others acquire mass, contributes a faint touch as well. These are the electro-weak corrections, and they are part of the total prediction we must include. Because the W and Z are so heavy, they are rare and reluctant visitors to the muon's cloak, and their contribution to the anomaly is tiny, far smaller than the QED piece. It shows up only in the deeper digits of the number, but it is unmistakably there, and crucially it can be calculated reliably. The electroweak theory is well tested and behaves gently in the same way QED does, with corrections that shrink as you climb the ladder of diagrams, so physicists can compute the electroweak contribution to high confidence, with an uncertainty small enough that it never drives the debate. There is something quietly marvellous in this. The muon's magnetism, this one number measured in a storage ring, is sensitive enough that the heaviest known forces leave a readable fingerprint on it. The same number that begins with Dirac's clean 2 and gains Schwinger's electromagnetic whisper also carries within it the faint signature of the force that lights the stars. To read the muon's anomaly to full precision is to take a census of every force in the everyday standard model at once. That sensitivity is exactly what makes the muon such a powerful test. If a force or a particle beyond the known three can touch the muon, it would add its own mark to the same number, sitting alongside the electromagnetic, the weak, and the strong contributions. The electroweak piece being calculable and small is good news, because it means it is not a source of confusion. We know it well, we add it in, and we move on with confidence. That leaves the third voice, the strong force, and it will not be dispatched so easily. Where the photon and the W and the Z gave us clean, shrinking corrections, the strong force gives us a tangle that the diagram ladder cannot climb. The largest source of doubt in the entire prediction lives here, in the contribution of the quarks and the gluons. To understand why this one piece is so hard, and why it would come to decide whether the muon was whispering of a new physics, or whether we had simply miscalculated, we have to look closely at the strong force and at what happens when a photon, near the muon, briefly turns into a storm of quarks. The strong nuclear force is the most powerful of the four forces, and the most reluctant to be calculated. It acts between quarks, the particles that make up protons and neutrons, and it is carried by particles called gluons. Its defining feature is strange and counterintuitive. The strong force does not weaken with distance the way gravity or electromagnetism does. It stays strong, or even grows, as quarks are pulled apart, which is why a quark can never be found wandering alone. Try to separate two quarks and the force between them only stiffens, until the energy you pour in conjures new quarks from the vacuum, and you end up with more bound particles rather than free ones. Quarks are forever confined inside the hadrons they build. This confinement is what makes the strong force so hard to compute for our purposes. The whole power of the Feynman diagram method rested on corrections that shrink as you climb, each loop smaller than the last because the relevant force was weak enough for that ladder to converge. The strong force, at the low energies that matter for the muon, is not weak. Its corrections do not shrink politely. The ladder does not converge. The very technique that conquered QED simply fails here, and physicists are left without their favourite tool exactly where they need it most. Now picture the specific thing the strong force does to the muon. In the vacuum's froth, the muon emits a virtual photon, as in Schwinger's simplest process. But that photon, before it returns, can briefly transform into a fleeting cloud of quarks and gluons, a tiny short-lived storm of strongly interacting matter, which then collapses back into a photon. This momentary detour through the world of quarks is called hadronic vacuum polarization. It is the strong force leaving its mark on the muon's magnetism, and it is the single largest source of uncertainty in the entire prediction. The everyday image that helps here is a stone dropped into a still pond. The photon is the stone, and for an instant it stirs up a churning patch of ripples and spray, the quark storm before the water settles again. Calculating the smooth flight of the stone is easy. Calculating exactly how much energy goes into that brief, complicated splash is the hard part, because the splash involves the strong force at its most untamed, all those quarks pulling on one another with a force that refuses to weaken. The size of this hadronic contribution is not small in the way the electroweak piece is small. It is the second largest contribution to the anomaly after QED itself. So getting it wrong does not nudge the prediction in some far decimal place. It shifts the prediction by an amount comparable to the very discrepancy that had everyone excited. This is precisely why the hadronic piece sits at the centre of the modern story. If this number is off, even by a little, the apparent gap between theory and experiment swells or shrinks accordingly. So physicists faced a genuine crisis of method. They had a contribution that mattered enormously, that they could not compute with their trusted ladder of diagrams, and whose uncertainty dominated everything. To make progress, they needed an entirely different way to get at the hadronic vacuum polarization, a way around the wall that confinement had built. Remarkably, two such ways exist, and the disagreement between them is where this whole story will finally turn. The first way is the oldest, and, for decades, the most trusted. Instead of calculating the quark storm from scratch, you go out and measure something closely related in the real world, in a particle collider, and use that measurement to stand in for the calculation you cannot do. If you cannot calculate the quark storm, you can try to measure it, and that is the idea behind the first and oldest method for the hadronic contribution. It rests on a beautiful piece of physics. The same quark storm that the virtual photon stirs up inside the muon's cloak is, in a sense, the very thing that happens when you collide an electron and a positron and watch them turn into hadrons. The process you cannot compute and the process you can measure are two views of the same underlying physics, linked by a deep mathematical relationship. So physicists go to colliders, they smash electrons into positrons at carefully chosen energies, and the two annihilate into a flash of energy that materializes as quarks, which then bind into hadrons that fly out and are detected. By counting how often this happens at each collision energy, and comparing it to a simpler reference process, they build up a quantity often called the R ratio, a map of how readily the vacuum produces hadrons across a whole range of energies. That map, fed through the mathematical link, yields the hadronic vacuum polarization for the muon. This is the data-driven method, and it turns an impossible calculation into a careful measurement. A long line of experiments has supplied this data over the decades. There were detectors at Novosibirsk in Russia, with names like CMD and SND, taking data at the lower energies that matter most. There was the KLOE experiment at Frascati in Italy, and the Babar experiment in California, and the Bessy experiment in China. Each measured the rate of electron-positron collisions turning into hadrons across its accessible energies, and together they painted the map the method needs. It was a vast, patient international labour accumulated over many years. One channel of this map matters more than any other. At low collision energies, the most common outcome is that the annihilation produces just two particles called pions, the lightest hadrons. This 2-pion channel dominates the hadronic contribution to the muon's anomaly, supplying the lion's share of it. So the precision of the whole prediction comes to rest, more than anywhere else, on how accurately the experiments have measured the rate of electron-positron pairs turning into 2 pions. Hold on to that fact, because a disagreement in exactly this channel will become the crack through which the whole story shifts. For a long time, this data-driven method was the gold standard. It was rooted in real measurements rather than an untamed calculation, and the various experiments broadly agreed, so physicists trusted the hadronic number it produced. When they added it to the rock-solid QED piece and the small electroweak piece, they had a complete prediction for the muon's anomaly, with the uncertainty dominated by this hadronic part but small enough to compare meaningfully against experiment. It was this complete data-driven prediction that for years sat below the measured value of the muon's magnetism. The muon appeared more magnetic than the standard model said it should be, and the gap was just large enough and just stubborn enough to look like it might be real. With the QED and electroweak pieces beyond reproach, suspicion fell either on new physics tugging at the muon, or on this hadronic number being slightly too small. For a long time, the smart money leaned toward new physics. There is one more hadronic effect to account for before the prediction is complete, smaller than the vacuum polarization, but even trickier in its own way. It involves not one photon turning into a quark storm, but light itself scattering off light through a loop of quarks, and it carried its own long history of difficulty. There is a second way the strong force touches the muon, rarer and subtler than the first, and for a long time it was the most feared term in the whole calculation. It is called hadronic light-by-light scattering, and to picture it you have to accept something that sounds impossible at first. Two beams of light, crossing in a vacuum, normally pass straight through each other without the slightest effect. Light does not bounce off light, and yet, through the quantum froth, light can scatter off light, very faintly, and that faint effect leaves its own mark on the muon's magnetism. The way it happens is this. Near the muon, several virtual photons can meet at a loop of quarks, a tiny temporary ring of strongly interacting matter, and through that ring the photons effectively scatter off one another. It is as if four beams of light all converged on a single fleeting droplet of quark matter and bounced off it into new directions. This is the hadronic light-by-light contribution, and like the vacuum polarization it involves the strong force at its most untamed, which is what makes it so hard to pin down. For years this term could not be measured the way the vacuum polarization could. There was no simple collider process that mapped onto it cleanly, no R ratio to lean on, so physicists were forced to estimate it using models of how quarks behave inside hadrons, educated approximations rather than firm measurements or rigorous calculations. Different models gave somewhat different answers, and worse, it was hard to put an honest uncertainty on the result. For a long stretch, many feared that this poorly known term might be large enough to swallow any conclusion, that the muon's whisper might be drowned out by our ignorance of light scattering off light. The good news, earned over more recent years, is that this fear has eased. Two lines of attack converged on the problem. One used careful mathematical relationships, called dispersion relations, to tie the light-by-light effect to other measurable quantities, much as the vacuum polarization had been tied to collider data. The other used the brute force computational method we'll meet next, simulating the quark loop directly on supercomputers. As these approaches matured and began to agree, the hadronic light-by-light contribution settled down into a number that, while still difficult, is now known well enough that it no longer dominates the uncertainty. The most feared term turned out to be tractable after all, so the accounting of the muon's anomaly is now complete in its outline. Start with Dirac's clean value of 2, add the large, exquisitely calculated QED corrections from photons and light leptons, add the small, reliable electro-weak corrections from the W, the Z, and the Higgs. Add the hadronic vacuum polarization, the quark storm stirred up by a single photon, which is the dominant uncertainty, and add the hadronic light-by-light term, the faint scattering of light off light through a quark loop now under control. Sum these, and you have the standard model's prediction for how magnetic the muon should be. The remaining doubt, the place where the prediction could be quietly wrong, lives almost entirely in that hadronic vacuum polarization, the quark storm. Everything else is either bedrock or small. This is the lesson to carry out of the theory side of the story. If the muon's measured magnetism disagrees with the prediction, the most likely culprits are either a genuine new particle or a slightly mistaken value for the quark storm. Which of those it is becomes the question of the age. But a prediction is only half of a test. We have spent these chapters building the number theory expects. Now we have to go and measure the real muon, to weigh its magnetism in the world, and that measurement has its own long and beautiful history, beginning with a set of rings built at a laboratory in Europe more than half a century ago. To measure the muon's magnetism, you cannot trap a single one and watch it for months as you can an electron, because the muon dies in about 2/millionths of a second. So physicists took a completely different approach, one that turns the muon's spin into a kind of clock you can read. The method was pioneered in a series of experiments at CERN, the great European laboratory near Geneva, beginning in the late 1950s and continuing through the 1970s. Those experiments invented the technique that every later measurement at Brookhaven and at Fermilab would inherit. The idea begins with making the muons all point the same way. When muons are produced in the right kind of particle decay, they come out naturally polarized, meaning their spins are lined up in a common direction, like a crowd of tiny compass needles all aimed together. This is a gift of the weak force and the way it produces muons, and it means physicists start with a beam of muons whose magnetism points a known way. That shared direction is the hand of the clock they will watch. Next, you send these spinning muons into a magnetic field and let them travel in a circle. Two things then turn. The muon's direction of motion sweeps around the circle, and the muon's spin, its little compass needle, also turns, because a magnet in a magnetic field feels a twist. The crucial point is that these two rotations need not keep pace. If the muon's g-factor were exactly 2, the spin would turn at precisely the same rate as the direction of motion, and the needle would always point the same way relative to the muon's path. The two would stay locked together, but the g-factor is not exactly 2. It is 2 plus the small anomaly, and that tiny surplus means the spin turns just slightly faster than the direction of motion. Over many laps, the muon's spin slowly creeps ahead of its motion, gaining a little each time around. The rate of that creeping, the speed at which the spin gets ahead of the path, depends directly on the anomaly. This slow drift is called the anomalous precession, and measuring its rate is exactly the same as measuring the surplus of g above 2. The experiment turns an abstract number into a frequency you can clock. The CERN experiments built this idea up in stages across 3 generations of increasingly refined machines. The first showed the technique could work at all. The later ones sent muons around proper storage rings and measured the anomalous precession with growing precision. By the time the CERN program concluded, it had confirmed Schwinger's leading correction and the higher QED terms beyond it, and had even reached the precision where the small electroweak contribution started to matter. The muon's anomaly was no longer just a calculated number. It was a measured one, and theory and measurement agreed. There is a lovely subtlety that the CERN physicist worked out, and that every later experiment relied on, concerning how the electric fields used to hold the muons in place might disturb the delicate precession. They found that at one special muon energy, a particular sweet spot, the disturbing effect of those electric fields very nearly cancels out of the precession. Running the muons at exactly that magic energy lets you focus the beam without spoiling the measurement. This trick, born at CERN, would be carried forward to Brookhaven and Fermilab unchanged, a piece of hard-won wisdom passed down the generations. So by the close of the 1970s, the essential method was complete and proven. Polarize the muons, store them in a ring, and watch how fast their spins drift ahead of their motion. That drift rate is the anomaly, measured directly. The CERN experiments had built the instrument and shown it worked, agreeing with theory at the precision of their day. The natural next step was to push that precision far higher, fine enough to test not just QED but the full standard model, and to go hunting for any disagreement that might betray new physics. That ambition would cross the Atlantic to a laboratory on Long Island, where a far larger and more precise ring was about to be built, and where the muon's whisper would first begin to sound like it might be saying something new. In the 1990s, the effort to weigh the muon's magnetism moved across the Atlantic to Brookhaven National Laboratory on Long Island, New York. The experiment there was called E821, and its ambition was to measure the muon's anomaly far more precisely than CERN ever had, precisely enough to test the full standard model and to notice if anything was missing from it. At the heart of E821 sat a single magnificent object, a circular magnet some 14 meters across, a ring of superconducting coils built to hold a magnetic field of extraordinary steadiness all the way around. The principle was the one CERN had perfected. Inject polarized muons into the ring, let them circle in the magnetic field, and measure how fast their spins drift ahead of their motion. But to reach the precision they wanted, the Brookhaven team had to control everything to a degree that borders on the obsessive. The magnetic field guiding the muons had to be known and uniform to a few parts in a million across the whole ring, because any patch where the field was a little stronger or weaker would falsely speed up or slow down the precession and corrupt the answer. Months of painstaking work, called shimming, went into smoothing that field to near perfection. There was the matter of keeping the muons inside the ring. A magnetic field alone bends them in a circle, but it does not stop them from drifting up or down, so the muons would spiral out of the storage region and be lost. To corral them vertically, the experiment used electric fields, electrostatic quadrupoles that gently focused the beam back toward the center. This solved one problem and created another, because electric fields can themselves twist a moving magnet's spin, and so disturb the very precession being measured. The escape from that trap was the magic energy that CERN had discovered. At one special muon momentum, near 3.1 giga-electron volts, the spin-twisting effect of the focusing electric fields very nearly cancels out, leaving the precession to reflect the magnetic field alone. Brookhaven ran its muons at exactly this magic momentum, so the electric fields could hold the beam in place without spoiling the measurement. It is a delicate piece of physics that a particular speed makes an unwanted effect vanish, and the whole experiment leaned on it. The muons themselves were made in stages. A beam of protons from Brookhaven's accelerator struck a target and produced pions, the light hadrons we met earlier. Those pions, flying forward, decayed in flight into muons, and because of the way the weak force works, the muons emerged neatly polarized, their spins aligned. These polarized muons were then guided into the storage ring, where they would circle thousands of times in the few microseconds before they decayed, each lap nudging their spin a little further ahead of their motion. Around the inside of the ring sat detectors, waiting. Their job was to catch the particles the muons threw off when they died, and from the timing of those decays to reconstruct how the muon spins had been pointing as the laps went by. The full machine was a marriage of a beautifully uniform magnet, a cloud of focused polarized muons and a ring of patient detectors, all aimed at reading a single tiny frequency to the last decimal place that human care could reach. Brookhaven ran E821 through the late 1990s and into the early 2000s, accumulating muon after muon, lap after lap. It pushed the precision well beyond CERN's, into the realm where the small hadronic uncertainty in the prediction became the thing that mattered, and as the result took shape, it began to sit slightly, stubbornly, above the predicted value. The muon looked a touch more magnetic than the standard model said it should be. Before we follow that gap and what it seemed to mean, we should understand more closely how the experiment actually turned a dying muon into a reading of its spin. The reading rests on the slow drift we have met before, the anomalous precession, so it is worth seeing exactly what is turning and why. A muon in the storage ring is doing two things at once. It is racing around the great circle, its direction of motion sweeping through a full turn each lap. And its spin, the little compass needle of its magnetism, is also rotating, because a magnet sitting in a magnetic field feels a twist that makes it precess, the way a spinning top wobbles slowly around the vertical under gravity. If the muon's g-factor were exactly 2, these two rotations would turn at precisely the same rate. The spin would stay locked to the motion, always pointing the same way relative to the direction the muon was travelling lap after lap. There would be nothing to measure, because nothing would change. The clean Dirac value would show up as perfect lockstep between spin and path. Because the g-factor is 2 plus the small anomaly, the lockstep is broken. The spin precesses just slightly faster than the direction of motion turns. Each lap, the muon's spin gains a tiny lead over its path, creeping ahead by a sliver. Over many laps, that sliver accumulates, and the spin slowly walks all the way around relative to the motion, again and again. The rate of that walking, the frequency at which the spin laps the motion, is called the anomalous precession frequency, and it is set directly by the anomaly. Measure that one frequency, and you have measured the surplus of g above 2. It is a remarkably clean idea. The whole subtle question of how the vacuum dresses the muon, all the QED and electroweak and hadronic contributions we spent chapters building, comes down in the end to how fast a spin drifts ahead of a path inside a magnet. The experiment does not need to measure the magnetism directly. It needs to measure a frequency, a rate of turning, which is among the things physicists know best how to measure with great precision. There is a second frequency the experiment must know just as well, the strength of the magnetic field that drives the precession. The drift rate alone is not enough, because how fast the spin precesses depends both on the anomaly and on how strong the field is. To extract the anomaly cleanly, you compare the muon's precession against an independent, exquisitely precise measurement of the magnetic field, made by watching how protons in a small sample precess in that same field. The anomaly emerges from the ratio of the two, the muon's drift against the field's strength. This is why the field had to be shimmed to a few parts in a million. The anomaly hides in the comparison of two frequencies, and any error in knowing the field feeds straight into the answer. The muon's drift is the signal, and the proton's response to the same field is the ruler, and the precision of the whole result is no better than the precision of that ruler. So the experiment reduces to clocking two delicate rhythms, the slow walk of the muon's spin ahead of its motion, and the steady response of protons that gauges the field. Hold those two rhythms tightly enough, and the anomaly falls out to many digits. But there is still the matter of how you actually see which way a given muon's spin is pointing as it circles, since you cannot watch a single muon's needle directly. The answer comes from the muon's death, and from one of the strangest facts in all of physics. To read which way a muon's spin is pointing, physicists exploit the way the muon dies. A muon does not simply wink out, it decays, transforming through the weak force into a lighter electron or positron, and a pair of nearly invisible neutrinos. For the positively charged muons used in these experiments, the visible product is a positron, the antimatter twin of the electron, which carries away some of the muon's energy and flies off in some direction, and the direction it flies is the key to everything. Here is the strange fact. When a muon decays, the positron does not come out evenly in all directions. It is preferentially thrown in the direction the muon's spin was pointing, especially the most energetic positrons. The muon's spin acts like a tiny launcher, biasing the decay toward its own axis. So if you catch a decay positron and note which way it came out, you have learned something about which way the parent muon's spin was aimed in the instant it died. The dying muon points, and the positron records the direction. This behaviour comes from a deep asymmetry in the weak force, the property called parity violation. For a long time, physicists assumed that nature treats left and right perfectly even-handedly, that any process and its mirror image are equally likely. In 1956, Zhongdao Li and Chenning Yang questioned that assumption for the weak force, and Qiansheng Wu, in a careful experiment with cooled cobalt nuclei, showed they were right. The weak force is lopsided. It distinguishes left from right, and because muon decay is governed by the weak force, the positrons it emits carry that lopsidedness, coming out preferentially along the spin. Now put this together with the storage ring. Billions of polarized muons circle the ring, their spins all slowly precessing, drifting ahead of their motion at the anomalous rate. As each muon decays, it flings a positron in the direction its spin happened to be pointing at that moment. The detectors around the ring count the high-energy positrons that reach them. When most of the spins point toward the detectors, many positrons are caught. A little later, when the precessing spins have rotated to point away, fewer positrons arrive. As the spins wheel around, the count of detected positrons rises and falls. The result, when you plot the number of detected positrons against time, is one of the most beautiful pictures in experimental physics. It is a curve that falls away overall, because the muons are steadily dying off and growing fewer, but riding on that fall is a gentle wiggle, a rhythmic rise and fall in the positron count. That wiggle is the muon's spin precessing, made visible. Its rhythm is the anomalous precession frequency, the very quantity that encodes the anomaly. The drift of the spin, invisible in itself, is written plainly in the timing of the deaths. Physicists call it the wiggle plot, and from the spacing of its waves they read the anomalous frequency to many digits. The fragile, short-lived muon, which seemed impossible to study at leisure, turns out to announce the direction of its spin in the very act of dying, and to do it billions of times so the statistics pile up. The weak force's lopsidedness, discovered in an entirely different context, becomes the tool that makes the whole measurement possible. So Brookhaven had its method complete. Store polarized muons, let their spins drift, and read that drift in the rhythm of the decay positrons against the precisely known field. As the wiggle plots accumulated and the frequency sharpened, the answer firmed up, and it kept landing a little above what the standard model predicted. By the time Brookhaven published its final result in the early 2000s, the measurement of the muon's anomaly had reached a precision of better than 1 part in a million. When the experimenters laid their measured value beside the best standard model prediction of the day, the two did not quite match. The measured magnetism of the muon sat a little above the predicted value, by an amount that was small in absolute terms but stubbornly larger than the combined uncertainties seemed to allow. Physicists measure the seriousness of such a gap in units called standard deviations, often written with the Greek letter sigma. A gap of 1 sigma is nothing, the kind of wobble you expect from ordinary chance. A gap of 2 or 3 sigma is interesting but not yet convincing, the sort of thing that sometimes melts away with more data. The threshold the field insists on before claiming a genuine discovery is 5 sigma, a gap so large that the odds of it arising by chance are smaller than 1 in a million. The Brookhaven gap came in at around 3 sigma, depending on exactly how the prediction was reckoned. 3 sigma is a tantalizing place to sit. It is too large to dismiss as a fluke, and too small to celebrate as a discovery. It is the size of gap that has, many times in the history of physics, turned out to be nothing more than an underestimated uncertainty or a subtle flaw somewhere in the analysis. But it is also the size of gap that has, on other occasions, been the first faint sign of something real and new. From the outside, the two cases look identical. Only more data and better calculation can tell them apart. What made the Brookhaven gap so exciting was where it pointed. Recall that the muon is a magnifying glass for heavy unknown particles, far more sensitive than the electron. If some particle beyond the standard model existed, light enough to flicker into the vacuum around the muon, it would add a little to the muon's anomaly and push the measured value above the prediction. That is exactly the direction the Brookhaven result leaned. The muon looked more magnetic than the known forces could account for, precisely as a new particle tugging on it would make it look. So the 3 sigma gap became one of the most discussed anomalies in particle physics. It was just the kind of hint theorists dream of, a small but persistent crack in the standard model that might be the doorway to something larger. Many wondered whether the muon was feeling the touch of particles predicted by theories like supersymmetry, which proposes a whole family of undiscovered partner particles. If those existed at the right masses, they could produce just such a surplus in the muon's magnetism. But the careful voices in the field kept pointing at the other possible source of the gap. The prediction the measurement was compared against contained that one stubborn, hard-to-calculate piece, the hadronic vacuum polarization, the quark storm. Its uncertainty dominated the theoretical side. If that hadronic number had been estimated a little too small, the prediction would come out too low, and the muon would appear too magnetic, mimicking new physics exactly. The gap could be a window onto the unknown, or it could be a flaw in the hardest calculation in the problem. This was the unsettled state Brookhaven left behind. A real, repeatable gap of about 3 sigma, pointing in the direction new physics would point, but resting on a prediction whose weakest part could plausibly explain the whole thing. To decide between these, the field needed 2 things. It needed a new measurement, more precise than Brookhaven's to sharpen the experimental value, and it needed the hadronic calculation pinned down by a method that did not depend on the old assumptions. The first of those would require a new and much improved experiment, and rather than build a new ring from scratch, physicists decided to move the old one. The superconducting storage ring at the centre of Brookhaven's experiment was a singular object, 50 feet across. Its coils wound and shimmed over years into a magnet of rare uniformity. To build another like it would have cost a fortune and taken many years. So when the next generation experiment was planned, to be hosted at Fermilab outside Chicago, the physicists made a bold decision. They would not build a new ring. They would move the existing one, intact, more than 3,000 miles from Long Island to Illinois. The ring could not be taken apart. Its delicate coils had to stay in their precise circular shape, because disturbing them would have ruined the painstaking uniformity that made the magnet useful. The whole great circle, more than 15 meters across, had to travel as a single rigid piece, kept flat and unflexed the entire way, never bent or twisted by more than a tiny tolerance, or the superconducting wires inside might be damaged beyond repair. It was a fragile giant that had to cross half a continent without so much as a wrench. The route was chosen to avoid the jolting of roads as much as possible. In the summer of 2013, the ring was sealed onto a special support structure, wrapped against the weather, and loaded onto a barge. It travelled by water down the east coast of the United States, around the tip of Florida, and up into the Gulf, then up the Mississippi and Illinois river systems toward Chicago, a long, slow voyage by sea and river. For the final stretch over land, it rode on a specially built truck that crept along closed highways at night, moving slowly enough to keep the precious circle from flexing. The journey covered about 3,200 miles in all. The wrapped ring, glowing under escort lights as it inched along darkened roads, became a small public sensation. People came out to watch the strange white circle pass and followed its progress online. For a piece of fundamental physics equipment, it drew a remarkable amount of attention, a giant electromagnet on a midnight road trip, carrying with it one of the most interesting unanswered questions in science. It arrived at Fermilab safely, its coils unharmed, ready to be made the heart of a new experiment. There was something fitting in the move. The same ring that had sat a little above the standard model at Brookhaven would now be rebuilt with far better surrounding equipment to test that very gap with much greater precision. The physical continuity mattered too. By reusing the exact magnet, the new experiment could be compared against the old one cleanly. The same ring asking the same question with sharper tools. 3 generations of the experiment, from CERN to Brookhaven to Fermilab, would share this lineage of method, and now Brookhaven and Fermilab would literally share the ring. The decision to move rather than rebuild also says something about how this kind of science works. The truly hard part of the Brookhaven magnet was not the idea, but the execution. The years of shimming that coaxed the field into uniformity. That investment lived in the physical coils themselves, in their exact wound geometry, and it was cheaper and surer to carry that geometry across a continent than to recreate it. Knowledge in this case was embodied in an object, and the object had to be moved. At Fermilab, the ring would be installed in a new building, surrounded by new detectors and a new and more intense source of muons, and shimmed all over again to an even finer uniformity than before. The experiment was named E989, the Fermilab Muon G2 experiment, and its goal was to measure the anomaly several times more precisely than Brookhaven had, sharp enough to turn that tantalizing 3 sigma gap into either a fading ghost or a real discovery. First, though, the old ring had to be brought back to life and its field made more perfect than ever. Once the ring reached Fermilab, the work of rebuilding began, and at its centre was the same task that had consumed the Brookhaven team, making the magnetic field uniform. The new experiment aimed for a field of about 1.5 Tesla, steady to a few parts in a million all the way around the ring, even finer than before. Achieving that meant shimming all over again, the slow art of placing small pieces of iron and fine adjustments around the magnet to iron out every bump and dip in the field, until the muons everywhere in the ring would feel as nearly the same field as human care could arrange. The shimming took the better part of a year, a quiet, meticulous labour far from the drama of the ring's journey. Physicists mapped the field with exquisitely sensitive probes, found the places where it strayed, nudged it back, and measured again, around and around, tightening the uniformity step by step. They reached a steadiness even better than Brookhaven had managed, the most uniform field of its size ever created. Only on that foundation could the precession be read cleanly, because as before, any unevenness in the field would masquerade as a change in the muon's drift and corrupt the answer. Around the perfected magnet, the team installed a new generation of detectors to catch the decay positrons, including detectors that could track individual particles inside the vacuum of the ring. They built a more intense and cleaner source of muons, fed by Fermilab's powerful accelerator complex, so that far more muons could be stored and far more decays recorded than at Brookhaven. More muons mean more wiggles counted, and more counts mean a sharper measurement, since the statistical uncertainty shrinks as the pile of data grows. The Fermilab muons were made much as Brookhaven's had been. Protons struck a target to make pions, the pions decayed in flight into polarized muons, and the muons selected at the magic momentum near 3.1 giga-electron volts were injected into the ring. There they circled, their spins precessing, focused vertically by electrostatic quadrupoles, whose spin-twisting effect the magic momentum was chosen to cancel. Every piece of hard-won technique from CERN and Brookhaven was carried forward, refined but unchanged in essence. The Fermilab Muon G2 experiment started taking physics data on the 31st of May 2017. It would run for several years, gathering data in a series of campaigns the collaboration called runs, each adding to the growing pile of recorded muon decays. By the end, the experiment would record on the order of 100 billion Muon decays, more than 20 times the statistics Brookhaven had managed. Each run brought improvements to the beam and the equipment, reducing the small systematic effects that could bias the result, so that later runs yielded cleaner data than earlier ones. The scale of the effort was enormous. The collaboration numbered in the hundreds, drawn from many countries, each person responsible for some corner of the vast machine, from the field maps to the detector calibrations to the analysis of the wiggle. Measuring a single number to better than a part in a million is not the work of a lone genius at a desk. It is the work of a small army, each member chipping away at one source of uncertainty, all of it eventually summed into one result. And as the data accumulated, the collaboration faced a danger that has nothing to do with magnets or muons, and everything to do with human nature. They knew, all of them, what answer they were hoping for or fearing. They knew the Brookhaven gap, knew that confirming it would be thrilling, and that erasing it would be a different kind of important. That knowledge is precisely what can lead a well-meaning team to fool itself, to nudge an analysis, however unconsciously, toward the answer it expects. To guard against exactly this, the experiment hid the answer from the very people measuring it. The danger is subtle and very human. When you know what result you're hoping to find, you can fool yourself without ever meaning to. Faced with a choice in the analysis, a cut to make here, a correction to apply there, you may lean, just slightly, toward the choices that nudge the answer toward what you expect. No dishonesty is required, only the ordinary human tendency to stop checking once the number looks right, and to keep checking when it looks wrong. Across hundreds of small decisions, that bias can quietly shift a result. Physicists have learned to fear it. The defense against it is called blinding, and the Fermilab experiment blinded itself in a thorough and clever way. The crucial quantity in the analysis is a frequency, the rhythm of the wiggle that gives the anomalous precession. The clocks that measured this frequency were deliberately set to the wrong rate by a secret amount, an offset known to no one on the analysis teams. A small number of people sealed that secret offset, in some accounts written on paper and locked away, untouched while the work went on. So the physicists analysing the data could do all their work, refine all their methods, and produce a value for the precession, but the value they saw was not the true one. It was shifted by the hidden offset, scrambled away from the real answer by an unknown amount. They could compare their analysis to itself, check that different methods agreed with one another, hunt down every systematic effect, all without ever seeing where the true number actually fell. They were working in the dark on purpose, and the darkness protected them from their own hopes. It went further. The collaboration ran several independent analysis teams in parallel, each developing its own software and its own methods to extract the frequency from the same data. If they had all seen the true answer, they might have unconsciously drifted toward agreeing with one another. Blinded, each team had to get its method right on its own merits, and only the consistency of their blinded results could reassure them. The blinding kept not just individuals but the whole group honest. Only when everything was finished, every check passed, every systematic effect accounted for, every team's analysis locked and frozen so that nothing more could be changed, did they unblind. In a gathering of the collaboration, the secret offset was revealed and applied, and for the first time the true value of the Muon's anomaly appeared on the screen. By then it was too late for anyone's expectations to bias the result, because the analysis was already fixed. Whatever the number was, they were bound to report it. This is worth dwelling on because it speaks to what makes a measurement trustworthy. The point of blinding is to remove the experimenter from the answer, to build a wall between what people hope for and what the data say. It is an act of institutional humility, a recognition that even the most careful and honest scientists can be misled by their own minds, and that the only sure guard is to make self-deception structurally impossible. The Fermilab team did not trust themselves to be unbiased. They engineered their ignorance so they would not have to. When the first Fermilab result was unblinded, the room held its breath, and then there was a burst of feeling, because the secret number, once revealed, landed very close to where Brookhaven had been. The gap had not gone away. The new, more careful, blinded measurement agreed with the old one and pulled in the same direction, above the prediction. After all the precautions against fooling themselves, the physicists found the anomaly still there, and now harder than ever to dismiss. The first Fermilab result was announced in April of 2021, based on the data from the first run, a small fraction of what the experiment would eventually collect. The world had been waiting for it, because everyone understood the stakes. If the new measurement confirmed Brookhaven, the gap with the standard model would harden into something serious. If it disagreed, the whole anomaly might dissolve. The announcement was watched live by physicists around the globe, an unusual level of public attention for the unveiling of a single number. The number confirmed Brookhaven. The Fermilab measurement of the Muon's anomaly landed essentially on top of the old Brookhaven value, with a similar precision, the two independent experiments agreeing closely. When the two results were combined into a world average, the experimental value of the muon's magnetism was now known better than either alone, and it sat clearly above the standard model prediction that the theory community had agreed upon the year before. The muon really did appear more magnetic than the known forces seemed able to explain. Against that agreed prediction, the gap between measurement and theory now stood at about 4.2 standard deviations. This was a striking number. It was well beyond the 3 sigma of Brookhaven alone, pushed up by the combination of the two experiments and the sharpened prediction. It was not yet the 5 sigma that the field demands before declaring a discovery, but it was close enough to feel within reach. Many physicists allowed themselves to believe that the muon was, at last, showing the first solid crack in the standard model, the long-sought sign of physics beyond it. The excitement was real and widespread. For decades, the standard model had withstood every test thrown at it, frustratingly complete, offering no clear foothold for the deeper theory everyone believed must lie beyond. Here, perhaps, was that foothold. If the gap was real, something unknown was tugging on the muon, some new particle or force waiting to be identified, and the next runs of the experiment with far more data might push the gap past 5 sigma and turn the hint into a discovery. The mood in much of the community was that a breakthrough might be near. But the careful caveat, the one that had shadowed the anomaly from the start, was louder now than ever, because of what had happened on the theory side in the very same period. The 4.2 sigma gap was measured against a particular prediction, the consensus value the theory community had published in 2020. That prediction's weakest piece was, as always, the hadronic vacuum polarization, the quark storm, computed by the data-driven method from collider measurements. And at almost the same moment as the Fermilab result, a completely different way of computing that same hadronic piece produced a different answer, one that would unsettle everything. So the spring of 2021 held 2 things at once, in tension. There was the triumphant experimental confirmation. The gap hardened to 4.2 sigma against the agreed prediction, the muon apparently caught in the act of defying the standard model. And there was a quiet, growing doubt about whether that agreed prediction was right, whether the hadronic number it rested on had been too small all along. The experiment had done its job beautifully. The question was whether the theory it was being compared against could be trusted. To understand both the height of the excitement and the doubt that undercut it, we need to look at the prediction the gap was measured against, the consensus value the theory community had laboured to produce, and at the rival calculation that arrived to challenge it. In 2020, before the first Fermilab result, the theory community had done something admirable. More than 100 physicists spanning every group that worked on the muon's magnetism came together as the Muon G2 Theory Initiative to agree on a single best prediction for the anomaly. Rather than have rival numbers floating around, they pooled their methods and their judgment into one consensus value, published in a document that came to be called the White Paper. It was meant to be the prediction against which the experiments would be judged. That consensus prediction rested for its difficult hadronic piece on the data-driven method. the long labour of measuring electron-positron collisions into hadrons and turning them into the quark storm's contribution. It was the gold standard approach, grounded in real measurements, refined over decades, and broadly agreed upon. When this prediction was set beside the combined Brookhaven and Fermilab measurement, it fell short, and that shortfall was the 4.2 sigma gap. The white paper value made the muons measured magnetism look anomalous, so in the spring of 2021, the anomaly looked as real as it ever would. 2 independent experiments agreed. A consensus prediction from more than 100 theorists sat well below them. The gap was large and pointed exactly where new physics would point. It is no surprise that this was the moment of greatest excitement, when many in the field allowed themselves to think a discovery was at hand, and when the theory papers proposing explanations came in a flood. Those explanations reached for the great unsolved problems of physics. Some invoked supersymmetry, the long hypothesized family of partner particles, whose members, if they existed at the right masses, could supply just the missing magnetism the muon seemed to show. Others proposed entirely new particles, a new heavy cousin of the photon, or new carriers tied to the muon specifically, since the electron showed no such anomaly. The muon's gap became a magnet of its own, drawing in theorists eager to connect it to dark matter, to the unexplained pattern of particle masses, to whatever lay beyond the standard model. There was a reason the muon was such fertile ground. The standard model, for all its success, is plainly incomplete. It says nothing about dark matter, nothing about gravity, nothing about why the particles have the masses they do. Physicists have searched for cracks in it for decades, mostly in vain, smashing particles together at ever higher energies and finding only the standard model staring back. The muon's anomaly was one of the very few persistent hints that anything lay beyond, and a hint that came not from brute force collisions, but from a precise, low-energy measurement. That made it precious, and the temptation to believe in it was strong. But belief in the gap depended entirely on trusting the prediction it was measured against, and the foundation of that prediction, the data-driven hadronic number, was about to be challenged from 2 directions at once. The challenge would not come from any new measurement of the muon itself, whose experimental value was solid and getting solider. It would come from the theory side, from a different way of computing the quark storm, and from a new measurement of the very collider data the old method depended on. The first challenge was the one that arrived alongside the Fermilab result, a calculation that bypassed the colliders entirely and computed the quark storm from first principles on a supercomputer. It got a larger value for the hadronic piece, large enough to lift the prediction and shrink the gap, and it forced the whole field to ask whether the anomaly had been an illusion of a mistaken calculation all along. The challenge came from a method called lattice quantum chromodynamics, lattice QCD for short, and it is a genuinely different way of attacking the quark storm. Rather than measure collider data and convert it, lattice QCD computes the behavior of quarks and gluons directly from the fundamental equations of the strong force, with no experimental input for the hadronic piece at all. The trick is to replace smooth, continuous space and time with a fine grid, a lattice of points, and to have a supercomputer calculate how the quark fields behave at every point on that grid. It is an enormous numerical undertaking, a simulation of the strong force in a tiny box of space-time. For a long time, lattice QCD could not compete on this problem. The calculation was simply too demanding, and its uncertainty on the hadronic contribution was far larger than the data-driven methods, too large to matter for the muon. But computers grew more powerful, the numerical techniques grew more clever, and one collaboration in particular pushed the method to the precision the muon demanded. They were the Budapest-Marseille-Wuppertal collaboration, known by the initials of those cities as BMW, a team spanning several European institutions. In 2020, and in a refined form published in the journal Nature in 2021, BMW announced the first complete lattice QCD calculation of the hadronic vacuum polarization at the precision needed to test the muon, and their answer was not the same as the data-driven one. The BMW value for the quark storm was larger than the value the collider data had given. A larger hadronic contribution means a larger predicted anomaly, which means the muon's measured magnetism would no longer sit so far above the prediction. In BMW's reckoning, the gap with experiment shrank dramatically, close to vanishing. This was startling, because it offered a completely different reading of the whole situation. If BMW was right, then the muon was not anomalous at all. Its magnetism agreed with the standard model, and the famous 4.2 sigma gap was not a sign of new physics, but an artifact of a data-driven hadronic number that had been too small. The exciting crack in the standard model would close, not because the experiment was wrong, but because the prediction it had been compared against was off in exactly the hard piece everyone had always worried about. The phrase that captures the moment is the title of this whole story. We had perhaps been wrong about the muon's hidden magnetism, wrong to read its small surplus as the touch of unknown particles, when it may have been the known strong force all along, merely miscalculated. The thing that had looked like a doorway to new physics threatened to be a measure of how hard it is to compute the strong force, nothing more. The wonder did not vanish, but it changed its character entirely. Of course, a single calculation, however careful, does not overturn decades of trusted data-driven work on its own. BMW's results stood in tension not only with experiment's old interpretation, but with the data-driven prediction itself, the two methods now disagreeing about the value of the quark storm by a meaningful amount. One of them had to be wrong, or both had some unaccounted for error. The community faced a new and sharper question, no longer mainly about new physics, but about which calculation of the strong force to believe. So the story pivoted. The drama moved from the storage ring, where the experimental answer was now firm, to the harder ground of theory, where two respected methods gave two different predictions. Resolving the muon's anomaly would mean resolving that disagreement, understanding why lattice QCD and the collider data did not match, and deciding which one told the truth about the quark storm. The disagreement between the two methods was uncomfortable precisely because both were respectable. The data-driven approach had decades of refinement behind it, grounded in real measurements from many experiments that broadly agreed with one another. Lattice QCD computed the same quantity from first principles, with no reliance on those measurements, and a major collaboration had brought it to comparable precision. Yet they gave different values for the hadronic vacuum polarization, and the difference was large enough to decide whether the muon was anomalous or not. This reframed the entire problem. For 20 years, the central question had been whether the muon's magnetism revealed new physics. Now the central question became narrower and more technical, but just as deep. Which calculation of the strong force was correct? The muon's measured magnetism was no longer really in doubt, pinned down by Brookhaven and Fermilab to high precision and still being sharpened. What was in doubt was the prediction, and specifically that one hadronic piece, where two trusted methods now openly disagreed. It is worth appreciating how unusual and healthy this situation was. The field had two independent roads to the same number, and they did not agree, which meant at least one of them harbored an error or an underestimated uncertainty. Rather than a crisis, this is the kind of tension that drives science forward, because it cannot be papered over. Someone's calculation was wrong, and finding out whose would teach the field something real about the strong force, regardless of what it meant for new physics. The disagreement was a problem, but it was a productive problem. To pin down where the methods diverged, physicists developed a clever tool, comparing not just the final numbers but pieces of them. They learned to break the hadronic contribution into windows, separating the part that comes from quark storms lasting very short times from the part that comes from longer ones. By comparing the data-driven and lattice results, window by window, they could localize the disagreement, see in which regime the two methods parted ways, and aim their scrutiny there. The trouble, it emerged, lived mostly in a particular intermediate window, and the groups focused their efforts on understanding it. There was good news threaded through this. As more lattice groups turned to the problem, and as the windows were compared, the lattice calculations began to look increasingly solid in the regions where they could be checked, and the disagreement with the data-driven method sharpened into something specific rather than vague. The field was not just staring at two numbers that differed. It was understanding, piece by piece, where and how they differed, which is the first step toward learning who is right. The mystery was becoming tractable, and then suspicion began to fall, more and more, on the data-driven side, on the collider measurements themselves. That method's foundation was the experimental data on electron-positron collisions into hadrons, especially the dominant 2-pion channel. Those measurements had been made by several experiments over many years and had broadly agreed, which was why they were trusted. But broadly agreeing is not the same as perfectly agreeing, and there had long been some tension among the different 2-pion data sets, between the results from one experiment and another. If those measurements were not as reliable as believed, the data-driven prediction built on them could be subtly wrong. The matter came to a head when a new and very careful measurement of that crucial 2-pion channel arrived, and instead of settling the data-driven foundation, it shook it. The new result did not match the older measurements the consensus prediction had relied on, and it pointed the data-driven number in the direction of the lattice. The ground beneath the old prediction, the ground that had made the muon look anomalous, began to move. The new measurement came from an experiment called CMD3 at the Novosibirsk laboratory in Russia, one of the long line of detectors that had supplied the collider data for the data-driven method. In 2023, CMD3 published a fresh and very precise measurement of the crucial process: electron-positron collisions producing two pions, the channel that dominates the hadronic contribution to the muon's anomaly. This was exactly the measurement the whole data-driven prediction leaned on most heavily, made anew with improved technique. The CMD3 result was a surprise. It did not agree with the earlier measurements of the same process that the 2020 consensus had used. It found a somewhat higher rate of 2-pion production than the older data, including the influential measurements from the KLOE experiment in Italy and the Babar experiment in California, which themselves had never sat perfectly together. A higher rate in this channel means a larger hadronic contribution, which means a larger predicted anomaly, which pulls the prediction up toward the measured value. The CMD3 data, in other words, leaned the same way the lattice did. This deepened the puzzle in a particular way. The data-driven method's whole claim to authority was that it rested on solid, agreed-upon measurements. But here was a new, careful measurement of the most important channel disagreeing with the older ones. The various 2-pion data sets could not all be right, because they did not all agree with each other. And until that internal disagreement among the collider experiments was understood and resolved, the data-driven prediction could not be trusted to the precision the muon demanded. Its foundation had cracks that had been papered over and were now impossible to ignore. So by 2023, the situation had quietly transformed. The early reading, that the muon revealed new physics, rested on a data-driven prediction that now looked shaky from two independent directions. Lattice QCD, computing the quark storm from first principles, gave a larger value that erased most of the gap, and CMD3, remeasuring the key collider data, also pointed toward a larger value, while exposing genuine disagreement among the older measurements the consensus had used. Both challenges pushed the same way, toward a prediction that agreed with experiment and a muon that was not anomalous after all. It is important to be clear and honest about what this did and did not show. It did not prove that there is no new physics affecting the muon. What it did was undermine the claim that the muon's magnetism clearly disagreed with the standard model. The apparent disagreement had depended on a particular value of the hadronic piece, and that value was now in serious doubt, challenged by a first principles calculation and by a fresh measurement of the very data it was built on. You cannot claim a discovery against a prediction you no longer trust. This is the unglamorous reality of frontier physics, and there is a quiet honesty in it worth honouring. The exciting story, new particles tugging on the muon, gave way to a harder and less thrilling one, about the difficulty of computing the strong force and the difficulty of measuring collider cross-sections to a fraction of a percent. The wonder did not disappear, but it relocated from hypothetical new particles to the genuine, formidable challenge of pinning down the known strong force precisely enough to test the standard model at all. The field now needed two things to move forward. It needed the lattice calculations to be confirmed by independent groups, so that BMW's pioneering result did not stand alone, and it needed the experiments measuring the Tupian data to sort out their disagreements. The second of those is still in progress, but the first arrived, and as more lattice groups reported, they began to agree with one another and with BMW, building the independent consensus the field required. A single calculation, however careful, is never enough in physics. BMW's pioneering lattice result needed to be checked by other groups, working independently, with their own methods and their own choices, to be sure it was not the product of some hidden error peculiar to one team. So through the early 2020s, other lattice QCD collaborations turned their attention and their supercomputer time to the same quark storm, computing the hadronic vacuum polarization, or carefully chosen pieces of it, on their own grids. The window technique made this checking sharp and efficient. Rather than each group having to compute the entire hadronic contribution to the highest precision, they could compute particular windows, particular time regimes of the quark storm, and compare those directly between groups. A window is easier to control and to compare than the whole, so agreement or disagreement shows up cleanly. The groups computed the same windows and laid their numbers side by side, a direct test of whether independent lattice calculations agreed. By 2024, the answer was increasingly that they did. Collaborations including the RBC and UK QCD groups, working together, and the Mainz group in Germany, among others, produced lattice results that agreed with BMW within their uncertainties, window by window. The pioneering calculation was no longer standing alone. Several independent teams using lattice QCD were converging on the same larger value for the hadronic contribution, the value that lifted the prediction and closed the gap with experiment. The lattice was speaking with more than one voice now, and the voices agreed. This convergence mattered enormously for trust. When one group gets a surprising answer, it might be a mistake. When several independent groups with different implementations get the same answer, the case grows strong that the answer is real. The lattice value for the quark storm was earning the kind of credibility that the data-driven method had once held alone, built up through independent confirmation. The strong force, computed from first principles on supercomputers, was yielding a consistent number across the world's lattice collaborations. At the same time, the older data-driven foundation remained unsettled, with the CMD3 measurement disagreeing with the earlier collider data, and the internal tensions among the Tupian datasets still unresolved. So the two roads to the hadronic number had, in a sense, traded places. The lattice, once the uncertain newcomer, was now the increasingly solid and convergent method. The data-driven approach, once the gold standard, was now the one with an unexplained internal disagreement that had to be sorted out before its prediction could be trusted to the needed precision. None of this touched the experimental measurement of the muon itself, which continued on its own track, accumulating data and growing more precise, indifferent to the theoretical drama. The storage ring did not care which calculation of the strong force was right. It simply measured how fast the muon's spins drifted, run after run, piling up the 100 billion decays that would yield the final sharpest experimental value. And in 2025, with all its data in hand, the Fermilab collaboration prepared to deliver that final word. So the stage was set for the closing act. On the theory side, the lattice calculations had converged on a larger hadronic value, lifting the standard model prediction toward the measured value, while the data-driven foundation remained under repair. On the experimental side, the most precise measurement of the muon's magnetism ever made was about to be announced. The question was whether, when the final prediction, and the final measurement were laid side by side, the famous anomaly would survive or fade. On the 3rd of June 2025, the Fermilab Muon G2 collaboration announced its third and final measurement of the muon's anomaly, drawing on all the data the experiment had collected across its runs. This was the result the whole effort had been building toward: the sharpest measurement of the muon's magnetism ever made, the product of 100 billion muon decays, a perfected magnet, and years of careful analysis. A few weeks earlier, the collaboration had gathered to unblind it, applying the secret offset at last and seeing the true number for the first time. The final measurement reached a precision of 127 parts per billion. That figure deserves a moment of plain wonder. It means the muon's magnetism was determined to within about 1 part in 8 million, a precision finer than the experiment's own original design goal. To measure any property of a particle that lives 2/millionths of a second to better than a part in a million is an astonishing feat of human care, and the Fermilab result stands as the most precise measurement of the muon's anomaly that will exist for many years to come. The final value agreed beautifully with the experiment's own earlier results from 2021 and 2023, and with the old Brookhaven measurement before them. All of these independent measurements, across decades and across a continent, landed on the same value for the muon's magnetism, now pinned down more tightly than ever. The experimental side of the story was complete and rock solid. Whatever the muon's magnetism is, we now know it with extraordinary confidence, and that knowledge is not going to change. The decades-long lineage was honoured that same cycle when the Muon G2 experiment received the 2026 Breakthrough Prize in Fundamental Physics, recognising 3 generations of the effort, from the early rings at CERN through Brookhaven to Fermilab. It was an acknowledgement that the achievement lay in the measurement itself, in the patient refinement of a single technique across half a century until it yielded a number good to a part in millions. The prize celebrated the experiment regardless of what the number ultimately meant for new physics, because the measurement was a triumph in its own right. But a measurement is only half of a test, and the meaning of this beautiful number depended entirely on what it was compared against. The experimental value was now firmer than ever. The prediction was the part that had been moving, lifted by the converging lattice calculations toward the measured value. So the real question on that day in June was not what the experiment found, which surprised no one, but what happened when the final measurement was set beside the new, lattice-based prediction that the theory community had by then assembled. For that comparison, the theorists had done their work in parallel, gathering the converged lattice results and the rest of the contributions into an updated consensus prediction, a new white paper to replace the 2020 version. Where the old prediction had used the now doubtful data-driven hadronic value, the new one drew on the lattice calculations that multiple groups had confirmed. The updated prediction was therefore higher than the old one, lifted by the larger hadronic contribution, and the question was how it would line up against the experiment's final word. So the two halves of the story came together at last: the most precise measurement ever made of the muon's magnetism, and a freshly updated prediction built on a different, increasingly trusted calculation of the strong force. When they were laid side by side, the famous gap that had excited physicists for 20 years was no longer there in the way it had been. The anomaly, measured against the new prediction, had largely faded, and the muon's magnetism looked, after all, like the standard model said it should. The updated prediction came in the Muon G2 Theory Initiative's 2025 white paper, and it told a sober, clarifying story. Built on the converged lattice QCD calculations of the hadronic contribution, rather than the doubtful data-driven value, the new prediction shifted substantially upward toward the measured value. When the theorists compared this lattice-based prediction with the final experimental result, they found no significant tension between the standard model and experiment at the current level of precision. The gap that had stood for 20 years had, in this reckoning, essentially closed. This is what it means to say we were wrong about the muon's hidden magnetism. For 2 decades, the small surplus of the muon's magnetism above the simplest value looked like it might be the fingerprint of unknown particles, the long-sought crack in the standard model. The new understanding is that the surplus is very likely just the known forces, the same QED and electro-weak and strong force contributions we built up chapter by chapter, with the stubborn strong force piece finally computed correctly. The muon was not whispering of new physics. It was whispering all along about how hard the strong force is to calculate. There is a double meaning in being wrong here, and both halves are honest. We were wrong. Centuries of intuition were wrong to ever expect the muon's magnetism to be the clean value of 2, because the living vacuum dresses it in corrections. And more recently, much of the field was wrong to read the leftover gap as new physics, when it was really a flaw in the hardest calculation in the problem. The first error was corrected by Schwinger and the long climb of QED. The second was corrected by the lattice and by a hard look at the collider data. But the calm, careful telling requires one more honesty, and the physicists themselves insist on it. The anomaly has been severely undermined, but it is not yet definitively resolved. The lattice-based prediction agrees with experiment, but the data-driven foundation still carries its unexplained internal disagreement, the CMD3 measurement clashing with the older 2-pion data. Those tensions among the experimental inputs have not been fully understood, and the lattice prediction, while convergent, is still less precise than the experimental measurement, leaving room for the picture to sharpen further. The case for new physics has faded, but the bookkeeping of the strong force is not entirely closed. So the Muon story ends, for now, not with the discovery of new particles, but with something quieter and in its way more impressive. It ends with the known forces of nature accounting for the magnetism of a particle to about 1 part in a million, with experiment and theory agreeing once the hardest piece was computed correctly. It is a triumph of the standard model, demonstrated at a precision few corners of science ever reach, and a reminder of how much careful work stands behind the word agreement. There is a lesson in the way the field handled all this, and it is part of the wonder. No one buried the inconvenient lattice result to protect the exciting anomaly. No one ignored the CMD3 measurement because it complicated the story. The experiment blinded itself to avoid bias. The theorists pursued an independent method that undercut the thrilling interpretation, and the community followed the evidence toward the less glamorous answer. That willingness to be wrong, to let a beautiful anomaly fade when the evidence demanded it, is the quiet engine that makes the whole enterprise trustworthy. The hunt for new physics goes on, elsewhere and by other means, because the standard model is still plainly incomplete. But the muon's magnetism, for so long one of the brightest hopes for a crack in it, has settled into agreement. The window stayed shut. What remains is the astonishing fact of the measurement itself, and of what it took to understand it, and that is where we return to the beginning. Think again of the magnet on your refrigerator, the small pull you can feel in your fingers. We followed that pull down to a single electron, then across to its heavier cousin the muon, and asked a simple question. How strong a magnet is it? The simplest theory, Dirac's beautiful equation, gave a clean answer, a G-factor of exactly 2. And the universe answered back, almost 2, but not quite, a whisper more. The whole story has been about that whisper. It is not the touch of unknown particles, as we hoped for 20 years. It is the living vacuum writing itself into the muon. Every photon that flickers around the muon, every brief storm of quarks the strong force conjures, every faint visit of the heavy W and Z, all of it adds a little to the muon's magnetism, lifting the G-factor above 2 by an amount we can now calculate and measure and find in agreement. The surplus is the signature of empty space, which is not empty at all. So the title's question has a plain answer. The muon's hidden magnetism is real, and we were wrong about it twice, first in thinking it should be the clean value, and then in thinking its small excess was a sign of new physics. The excess is the known forces of nature, the same forces that light the stars and bind the nuclei, leaving their mark on one fragile particle's magnetism. To read that mark, and to understand it, took 3 generations of experiments, a magnet carried across a continent, 100 billion dying muons, and supercomputers simulating the strong force in a tiny box of space and time. There is something to carry out of this beyond the muon itself. We learned how a measurement to a part in a million is actually made by people who hid the answer from themselves so their hopes could not corrupt it. We learned how a thrilling anomaly can fade not through any single mistake, but through the slow, honest work of checking, and how the fading can be its own kind of triumph, the standard model vindicated at a precision almost beyond belief. The story did not give us new particles, it gave us a clearer view of how careful we can be, and the muon still has more to say. The experimental value is now fixed, but the theory is still sharpening, the lattice calculations growing more precise, the collider data being remeasured to resolve its disagreements. Should the prediction and the measurement ever drift apart again as both grow sharper, the window to new physics could reopen. Other experiments, like one being built in Japan with an entirely different technique, will measure the same magnetism in a new way and serve as a check. The question is quieter now, but it is not finished. Step back far enough and the wonder is simple. You're made of particles that are themselves tiny magnets, each one dressed in the restless activity of the vacuum, each one carrying in its magnetism a faint record of every force in nature. We took one such particle, the muon, and weighed its magnetism so precisely that we could read the vacuum's handwriting in it and check that handwriting against our deepest theory of how the world is built. That we can do this at all, that the universe is lawful enough and we are careful enough to measure a dying particle's magnetism to a part in millions and understand what we find is the real marvel. The pull on your refrigerator door, then, reaches all the way down to this. A point of charge, a fixed spin, a G-factor, a whisper above 2, and in that whisper, the living emptiness of space and the patient self-correcting work of people determined to get one number exactly right.